Imagine a giant factory where copper and aluminum, like two ancient titans, come together in a single dance of heat. The air here vibrates with precision. Coils spin at a speed that could twist time, and furnaces burn brighter than a sunset over the Sahara. Every hour, this mega complex produces hundreds of heat exchangers, the heart of every air conditioning system, refrigerator, or car. It all begins with the gleam of metal. Ready for a deep dive? Then let's head into the very core of production. To start manufacturing, we need to prepare the materials. Copper tubes are made from high-quality copper, often with internal spirals or microfin structures to improve turbulence and heat transfer. Before further processing, the tubes undergo cleaning and annealing to relieve internal stress. Aluminum fins are cut from aluminum alloys, such as 8006 or 1199, which have excellent thermal conductivity and corrosion resistance. The fins can have various shapes: straight, wavy, perforated, to optimize airflow and heat transfer. At large factories, especially in Asia, the United States, or Europe, where heat exchanger production is large-scale and automated, material preparation is part of the same complex. There are workshops that uncoil large spools of copper or aluminum wire, cut plates and tubes to the required length, surface treat them, and store the semi-finished products under controlled humidity and temperature conditions. In smaller production facilities, or in cases of clear specialization, for example, heat exchangers for aviation or military equipment, the blanks may be supplied already prepared from outside. This helps reduce equipment costs and allows focusing on precise assembly and testing. In a huge workshop, where only the rustle of metal and the precise clicking of mechanisms can be heard, the mystery of creating the heart of a heat exchanger, its core, begins. Thin aluminum fins, like metal scales, light, flexible, but with character, are fed onto the conveyor with millimeter precision. They have a complex geometry, corrugated, with microscopic slits that increase the heat exchange surface area, like a fan catching every breath of air. In parallel, from another line, copper tubes slowly slide down. Short, but very important segments, shiny after cleaning, strong and plastic at the same time. Their diameter is precisely matched to the fins. Each tube must pass through a series of holes in the fins, literally piercing the entire stack, like a thread gathering beads. This is done manually only in experimental production or in the early stages of development, but in most factories, this stage is fully automated. After stringing, mechanical expansion begins, a unique procedure where special mandrels are inserted into the tubes, or they are pressed from the inside with hydraulics. This expands the copper, and it presses tightly against the holes in the fins. The contact must not just be tight, it must be perfectly tight, because this is the area where heat will be transferred from the hot fluid to the cooling air or vice versa. Every microcrack is a loss of efficiency. In more complex or critical models, the tubes are also brazed to the fins, either in a furnace or by the induction method. The metal melts only on the surface, merging the aluminum and copper into a single structure. The assembled structure is inserted into a frame. On the sides, strong aluminum or steel supports, top and bottom, collectors that will gather and distribute the heat transfer fluid. This is now the core, which will undergo dozens more checks before it ends up in an air conditioner, car, or server cooler. When the core is assembled, a real test awaits it: brazing. First, the structure is prepared, cleaned of oils and contaminants left during assembly. This is done with special degreasers or washing solutions, because any particle of dirt is a potential enemy of quality connection. Then, a filler metal is applied to the brazing spots, a thin layer of alloy, most often aluminum or copper, which melts before the base metal. And here, the key moment: the furnace. Large, sealed like a vacuum capsule, it slowly swallows the blanks. Inside, an oxygen-free atmosphere, often with nitrogen or argon, to avoid oxidation. The temperature rises gradually to avoid creating stress in the metal. At its maximum, about 1,112 degrees Fahrenheit for aluminum, the filler metal begins to flow, but not boil. It fills the gaps, like liquid gold, penetrates the smallest crevices between the tubes and fins, binding everything together, like lava squeezing mountain rocks into a single block. This process is called diffusion brazing, extremely precise and uniform. The furnace can hold dozens or even hundreds of heat exchangers at a time, so each one undergoes processing under absolutely identical conditions. This guarantees stability, no overheating, no underbrazing, and it's also economically viable. After leaving the furnace, the structures shine like newly forged artifacts. Externally, nothing has changed, but inside, a transformation at the molecular level. This is no longer a set of parts, but a single body capable of withstanding years of operation, temperature changes, impacts, vibrations, and aggressive environments. While the heat exchangers are still hot, they are slowly cooled in a controlled environment. This is not just a technical procedure, it's a hardening ritual. If cooled too quickly, the metal structure will develop microcracks. If slowly, without control, the geometry will be compromised. So, after the fire comes water. After the insane temperature when the solder flowed between the aluminum and copper, the heat exchanger seems to take a breath. It has survived the hottest moment of its life. But ahead lies an equally responsible stage: cleaning, inspection, protection. First, the heat exchanger enters a washing zone. Here, the remnants of flux, the substance that helped the solder flow evenly and tightly, are washed off. If left, it could later cause corrosion or reduce the device's efficiency. Therefore, the part is bathed in special tanks, hot water, neutral solutions, sometimes ultrasonic cleaning, everything to make every millimeter shine with cleanliness. But beauty is not everything. Each heat exchanger is tested for leaks. Imagine air hoses being connected to it, submerging it in water, and applying pressure. Even a tiny bubble means a problem. Either a joint wasn't properly brazed, or a microcrack has formed, and then it's off for reprocessing. But if the water remains calm as a mirror, the product moves on. Strength is also checked by pressure, often higher than what the product will withstand in real conditions. After this, the final cosmetics. Aluminum elements may be anodized. This is an electrochemical process that creates an oxide film on the surface. It makes the material resistant to rust and adds an elegant matte sheen. Sometimes special protective coatings are applied, varnish or polymer paint, which not only adds color, but also protects against aggressive environments. The world is changing, and heat exchangers are changing with it. While classic copper tubes and aluminum fins still serve faithfully, new heroes are appearing on the horizon, with the strange gleam of future technologies. One such breakthrough is aluminum-clad copper tubes. Imagine this: lightweight and corrosion-resistant aluminum. On the outside and inside, a copper heart that conducts heat with incredible efficiency. This combination preserves the key advantages of both metals, minimizing their weaknesses. These tubes, like a perfect union of opposites working in harmony. They are easy to process, lighter than pure copper, cheaper, and yet provide thermal efficiency on par with top-tier solutions. But the brightest future belongs to 3D printing. In sterile laboratories, where printers don't apply ink but molten metal, structures are born that previously existed only in the fantasies of engineers. Here, they don't just copy familiar tubes and fins, they create new geometries, spirals, lattices, organic forms that mimic the microstructures of bones or leaves. They are lighter, more efficient, more compact, and they can be tailored to a specific device or operating condition down to the smallest detail. These printers can work with copper, stainless steel, and eventually, new generation composites. Such products cool processes faster, transfer heat more efficiently in electric vehicles, and last longer in harsh climatic conditions. And all this with fewer resource costs and minimal heat loss. Every hour worldwide, over 1,000 tons of copper are smelted, the metal that forms the foundation of civilization. It travels a path through thousands of degrees to become a simple rod. But behind this humble form lies an explosion of temperatures, fire, and precision down to the micron. Here, furnaces melt bronze at 1910 degrees Fahrenheit. Here, metal is processed, ground, stretched until it becomes perfect. All under the watchful eye of engineers, sensors, and fire. Today, you will see how the heart of technology is created, and it is spectacular. Every day around the world, metal that has traveled thousands of miles goes into furnaces and crucibles to become a rod, humble but indispensable. And it all begins with a copper heart, cathodes, ingots, and scrap. A copper ingot, heavy like a large suitcase. It blocks light and rings if you hit it. It weighs about 100 pounds, and its journey is just beginning. And here's a cathode, a plate the size of a door, up to 300 pounds, refined by electrolysis, almost pure copper. Its color is warm, deep, like the autumn sun at sunset. These giants, as well as fragments of old pipes, parts, and wires, all of this is dumped into the deep bunkers of the melting shop. For brass, zinc is added to copper. The soft red metal suddenly becomes golden, hard, and elastic. In classic recipes, 60% is copper and 40% is zinc, although the proportions can be adjusted. And if bronze is needed, copper is combined with tin, sometimes with aluminum, silicon, or phosphorus. Bronze is less flexible but more resistant. It was bronze that gave its name to an entire era, the Bronze Age. The classic formula is 88% copper, 12% tin. These numbers are not accidental. It's a precise balance. A little more, and the metal will be brittle. A little less, and it won't withstand any stressed structure. Everything that has just been gathered, copper cathodes, ingots, zinc bars, tin granules, is loaded into furnaces that know no mercy. These are either induction furnaces, where the metal is heated by an electromagnetic field, or gas-fired crucibles, where the flame can be heard even through thick walls. The temperatures here are hellish. Brass melts at 1700 degrees Fahrenheit. Bronze requires even more, up to 1910 degrees. The metal in liquid state, shining, heavy. It cannot be touched, only observed through special glasses. One careless movement, and half a ton of molten alloy can spill onto everything around. At this moment, fluxes are added to the melt, powders that help collect slag, meaning impurities, oxides, remnants of old metal. They float to the surface, forming foam or a crust, which is carefully removed. One melting crucible holds up to 10,000 pounds of metal. The temperature inside is controlled by thermocouples capable of withstanding 2,000 degrees Fahrenheit and more. In nearby laboratories, samples are constantly taken. It's like with winemakers. They check the chemical composition, test hardness, and prepare analytical charts. The metal hasn't become a rod yet, but it already has its passport. Metallurgists in protective suits, with masks on their faces and heat-resistant gloves, approach the furnace. On their faces is calm concentration. They are used to working near metal hotter than lava. All movements are honed, like in a dance where the price of a mistake is higher than anything else. The furnace tilts, or the bottom gate opens, and a stream of molten alloy erupts from its depths. It's bright yellow, as if the sun itself decided to turn liquid. The stream is directed into casting molds, special steel or graphite forms. They come in different shapes: square, round, hexagonal. Depending on what the future rod will be, the molds are already heated. If they are cold, the metal might kick back, splash, or crack. The temperature in them is above 500 degrees Fahrenheit, but this is minor for the world of metal. At the moment of pouring, the workshop falls silent. Everyone watches to see if it's flowing correctly, if no slag is getting in, if no air pockets are forming. Sometimes steam erupts from the mold. That's water left after the previous cooling. Steam hisses, mixes with the heat, smells of metal and earth. In foundry production, Molds, especially temporary ones, can be made of a sand-clay mixture reinforced with resins. When molten metal is poured into such molds, they char, burn, or evaporate moisture, and this gives off a smell similar to damp earth, ash, minerals after rain. Or before pouring, the molds might contain remnants of water or condensation. And when thousands of degrees suddenly hit a drop, steam with a mineral aroma is created. It smells like earth after a thunderstorm. The same effect, but in the workshop. It's hard to breathe in the workshop. Heat, dust, hot air rising, and underfoot. Layers of cooled bronze, brass, fine scrap. The floor glitters. Particles of alloy that didn't make it into the mold solidify immediately, forming a shiny crust. The molds fill up quickly, and the metal begins to cool. Slowly at first, then faster. Before your eyes, the magic of solidification. The molten river becomes a solid body. Bronze, a deep brown. Brass, yellow with a sheen, like fresh gold. When the metal starts to set, workers take long metal rods and smooth the surface, remove residual slag, and check the edges. Some laugh, joke, but keep one eye on the melt anyway. Here, it's important not to miss anything. After a few minutes, the molds are cooled with water or air. The rods are pushed or pulled out of the molds, still warm but already solid. They are steaming, hissing, as if surprised themselves that they have become a single body. As soon as the rods are removed from the molds, the next phase begins: processing. Hot, heavy, still smelling of metallic smoke, they head further into the hands of machines. First, cooling. If this isn't done, the alloy will continue to crystallize unevenly and cracks may appear. The rods are doused with streams of water or submerged in large baths. Water hisses, steam rises in a wall, the air becomes heavy and humid. The metal darkens but becomes harder. After this, they are directed to the cutting line. Each rod must have a precise length, say 10 feet. Robots trim the ends, uneven, melted, with excess material. The cut looks like a shiny mirror, from which crumbs of hot metal are dripping. The operator checks if the ends are even, if there are no voids visible inside. Next, rolling. This is one of the most impressive parts. The rods are passed through a system of rolls, huge metal cylinders rotating with a roar. This is where the precise diameter is formed. Whether it will be 5/8 of an inch or 3/4 depends on the order. The metal becomes thinner, longer, and more uniform. It's as if it's being drawn out before your eyes. At this point, pressure and temperature sensors are working, because even a rod overheated by a few degrees can warp or disrupt the structure. In the next stage, straightening. After rolling, the rods may still have minor bends. They are placed on a line with rotating rollers, where special hydraulic presses or automatic hammers straighten them to millimeter precision. After mechanical processing, surface finishing, the rods are ground or machined to remove scale, minor irregularities, microscopic inclusions. When they pass through polishing machines, it seems as if the metal comes alive. It starts to gleam, like a freshly polished brass pipe in a parade. And finally, checking the dimensions. Here, precision is like in surgery: calipers, laser scanners, digital gauges. 1 extra micron, and the whole batch can be rejected. When the rods already look perfect, the moment of truth arrives: calibration and testing. Each sample is checked for compliance with precise technical parameters. Laboratory technicians and engineers take over. They test the diameter, length, weight, hardness, flexibility, and even the microstructure of the metal. The rod is fed into calibrating machines with high-precision optics or lasers. They detect even slight deviations within fractions of a millimeter. Then a sample is taken from it for tensile testing. The metal is stretched to its limit until it breaks. This shows how much load the rod will withstand in real conditions. Another test: bending. It is clamped in special pliers and bent to a certain angle, checking whether cracks appear. Everything is recorded. If the rod fails, it is either remelted or scrapped. Only those that have passed the full cycle receive marking and move on. After testing, the rods are marked, packaged, and sent to warehouses or directly to customers. Some are wrapped in protective film, others stacked in wooden boxes or metal racks. They are sent to workshops where they will be manufactured into parts for technology, construction, and electronics. Every year, the world produces over hundreds of millions of artillery shells, complex and precise items that play a key role in modern armed forces. From the smallest shells to heavy 6-inch casings, each one goes through a complex path, from metal scrap to a powerful munition capable of changing the course of a battle. Huge factories work continuously, using the latest technologies and high-precision equipment to provide armies worldwide with reliable and effective weapons. In this video, we will delve into the process of manufacturing artillery shells. From metal processing and forming the casings to filling with explosives and testing the finished product. Get ready to see how millions of tiny details turn into a formidable weapon, and understand why this is so important for the security and defense capabilities of countries. Don't miss it. It will be spectacular and extremely interesting. The production of artillery shells begins with the selection and preparation of the metallic material. The basis for most shells is high-quality steel, which provides the necessary strength, heat resistance, and accuracy. Metal for blanks is usually supplied in the form of large rolls or sheets, with thickness ranging from a few tenths of an inch to several inches, depending on the caliber of the shell. In the United States, annual steel production is approximately 87 million tons, or about 96 billion pounds. From this enormous quantity, a certain portion goes to the defense industry, where the metal undergoes strict quality control and certification. For example, special alloy steel is used for artillery shells, which has increased strength and corrosion resistance. Blanks for shells are made at steel mills, where the metal is melted in large furnaces at temperatures exceeding 2,700 degrees Fahrenheit. After this, the molten metal is poured into molds, resulting in large plates or rectangular blocks. Then these plates are rolled on rolling mills, reducing the thickness to the required parameters, 2 inches and less. Rolling mills can be either hot or cold, depending on the processing stage. Hot rolled sheets have lower accuracy, but are easily formed, while cold rolled sheets are ideal for parts requiring high precision and a smooth surface finish. Next, the metal sheets or rolls are transported to munitions plants. Here, using equipment, the shell casings are cut from the blanks, tubular or cylindrical, depending on the type of munition. In 1 hour, a modern facility can process hundreds of thousands of pounds of metal, transforming it into hundreds of finished casings. To understand the scale, in 2022, the United States manufactured over 10 million artillery shells of various calibers. Considering that one shell casing weighs about 100 pounds, producing this quantity required over 1 billion pounds of special steel. Blanks arrive at the munitions plant, where their transformation into actual shells begins. Heavy spools of steel or other alloy, weighing several tons and stretching hundreds of feet long, are placed on special uncoiling platforms. These setups unwind the roll like a giant spool, feeding the steel strip further down the line. In the next stage, high-precision guillotine shears, or rotary disc cutters, are used to cut sheets or discs of precisely specified length and width from the roll. For shells of different calibers, from less than an inch to 6 inches, different sized blanks are needed, so the computer numerical control system adjusts the cutting parameters to the required standard. Next, the blanks are heated in industrial furnaces to a temperature of approximately 2,000 degrees Fahrenheit. The metal becomes plastic, like clay. It is transferred to hydraulic presses, where, under pressure of hundreds of tons, the future shells are given their initial shape, an elongated cylinder with a pointed end. After the metal blanks have undergone initial forming, usually by deep drawing or hot stamping, they are still far from ideal. The blanks come out slightly deformed, with excess length, an uneven edge, and micro bends. Therefore, the next stage is calibration and trimming. The hot part cools in special baths or under a stream of air, so the steel sets in its new shape. Then the shell is fed to a trimming machine. Rotating blades or milling cutters cut off the excess length. For example, for a large artillery shell, the typical casing length is 15.6 inches. This is accuracy not by eye, but to the thousandth of an inch. After this, the part passes through a calibrating unit. This is either crimping rolls or boring systems with precision micrometers. The casing diameter must match the standard plus or minus 0.001 inch. Otherwise, the shell will either not enter the gun's chamber or will get stuck. At the output, we have a part ready for further processing, with clear geometry and parameters. The blanks slowly move inside the computer numerical control machines, massive machines with gleaming tools rotating at speeds up to 15,000 revolutions per minute. Sharp milling cutters, resembling miniature circular saws, cut off excess metal with surgical precision, as if engraving the steel cylinder. Under the automatic aim, the location for the rotating band, a narrow groove that holds a copper ring, thanks to which the shell moves along the rifling of the gun's barrel. Then, threading for the fuse. The supply of coolant is accompanied by hissing and steam, sparks, steel, fog. Every turn of the tool transforms a formless blank into a high-precision shell. After milling, the shell casings are sent to the heat treatment stage. And this is, without exaggeration, a fiery forge of high technology. The blanks are submerged in furnaces where the temperature reaches over 1,600 degrees Fahrenheit. In a dark hall filled with the orange glow of the metal, giant furnaces heat the casings to a state where the steel becomes more flexible, loses stress, and acquires the necessary strength. After heating, rapid cooling. This is either an oil bath, streams of air, or water quenching. The choice depends on the type of alloy. The process is called hardening, and it's what transforms the shell casing from a simple blank into steel capable of withstanding the immense stress during firing. Next, grinding. Each casing passes through machines that, with a screeching sound, remove microns of remaining scale, irregularities, and excess material buildup. Streams of coolant create a mist, and the air smells of metal and machine oil. Workers in safety glasses carefully monitor each casing so as not to miss any micro cracks or deformations. After grinding, it's time to move on to the most important part, creating the explosive filling. Before this, the casings go through a degreasing and inspection stage again. Not a speck of dust or a drop of oil should remain inside, so as not to affect the stability of the explosive material. A component is installed in the rear part of the shell through which the charge will later be introduced, or it is sealed immediately if the design requires it. If it's a high explosive shell, the casing is filled with explosive material, usually TNT, octol, or a mixture like Composition B. The process can be casting, where molten explosive is poured into the casing, or pressing. This is an extremely delicate and controlled process. Everything happens automatically, with remote control and under the supervision of specialists in armored cabins. A socket for the fuse or the fuse itself is inserted into the nose part of the shell, either immediately before use or during manufacturing. Everything is sealed to prevent moisture from entering. In the final stage of manufacturing, artillery shells enter the paint booths, large rooms with exhaust fans, filters, and automated sprayers. Here, the shell casings are covered with a special paint that not only marks the type of munition, but also protects the metal from corrosion during storage or transport. The color matters. Yellow, for high explosive fragmentation, green, for smoke, black, for armor piercing, and blue often indicates training rounds. The paint is applied evenly, in a thin layer, usually in several passes, so as not to exceed the permissible weight of the shell. After drying, marking follows. Caliber, shell type, serial number, batch number, production date. This is done with a stencil or using an industrial printer. Every detail matters. Military personnel need to quickly identify exactly what they have in front of them, under what conditions it can be used, and from which batch it came. Imagine a material lighter than plastic, but 10 times stronger than steel. It's the stuff they use to make National Aeronautics and Space Administration rockets, high-performance race cars, and armor for fighter jets. But you know what the paradox is? This super material is almost impossible to recycle. Its production is mind-blowing. Scorching furnaces, molecular transformations, nanotubes, cold plasma. But what happens when these parts wear out or break? The world got hooked on carbon fiber, and now it doesn't quite know what to do with it. In this video, the whole truth about the strongest material of our time. Don't touch that dial. It's about to get even stronger. The production process for carbon fiber starts with getting the raw material, polymers, most often polyacrylonitrile. This polymer consists of long chains of molecules that undergo special processing to give them the necessary properties for later transformation into fiber. The first step is extrusion. The polymer is melted and forced through tiny holes, forming fibers about 3/millionths of an inch in diameter. These fibers are gathered into bundles, called tows, and prepared for the next stage, stabilization. Stabilization is a chemical process where the fibers are heated in the presence of oxygen at temperatures ranging from 400 degrees Fahrenheit to 600 degrees Fahrenheit. As a result, the polymer molecules change their structure, becoming more heat-resistant and ready for carbonization. The next and most crucial stage is carbonization. The fibers are heated in an oxygen-free environment to very high temperatures, from 200 to 500 degrees Fahrenheit. Under the influence of such temperatures, all the light elements like hydrogen, oxygen, and nitrogen evaporate from the fibers, leaving behind almost pure carbon. It's this process that gives the fibers their unique strength properties. After carbonization, the fibers might undergo additional treatment, such as applying a coating to improve adhesion with a composite matrix. The resulting carbon fibers are collected into fabrics or matrices of various structures. These can be unidirectional bundles, woven fabrics, rolls, and so on. The choice of structure depends on the final application and the required mechanical characteristics. Next, these fabrics are impregnated with special resins, epoxy, polyester, or others, which allows for the creation of a composite material, a carbon fiber reinforced polymer composite. This composite boasts high strength and rigidity while remaining lightweight. Lamination is the process of layering sheets of resin, impregnated carbon fiber fabric into a mold, where under pressure and heat, the resin polymerizes and the material hardens. The result is a strong, lightweight, and durable part in the desired shape. Thanks to its unique combination of lightness and strength, carbon fiber has found wide application in many fields. In automotive manufacturing, it's used for making body panels, suspension parts, and interior elements. This significantly reduces the car's weight, improves dynamics, and lowers fuel consumption. In aviation, carbon composites are used in fuselages, wings, and other structural components of aircraft. This increases fuel efficiency and reduces carbon emissions. In the space industry, the material is used in the production of rocket bodies, satellite panels, and elements of space stations. Carbon fiber withstands the extreme conditions of space and has high durability. Bicycles, tennis rackets, skis, boats, and even sportswear are made from carbon fiber to enhance performance characteristics. And reinforcing concrete structures with carbon composites increases their strength and resistance to corrosion. This material offers high strength at low weight. After all, carbon fiber is 5 or even 10 times stronger than steel, but significantly lighter. The fiber has excellent resistance to corrosion and chemical attacks. It also boasts high stiffness and resistance to material fatigue. Plus, it allows for the formation of complex shapes and parts, and it has thermal stability and a low coefficient of thermal expansion. But the high cost of production limits the use of carbon fiber in mass manufacturing. Also, the material is brittle and can fail under strong point impacts. Undoubtedly, carbon fiber is difficult to repair and recycle, and its mass use is also hindered by the energy intensity of the carbonization process. Carbon fiber continues to evolve thanks to innovations in production technologies and new areas of application. New carbon fiber production technologies aim to increase efficiency, reduce energy consumption and material cost, and expand the raw material base. One of the most promising discoveries is the cold plasma pyrolysis method, developed by David L. Chandler at the Massachusetts Institute of Technology. This process uses ionized gas at room temperature to break down polymer fibers into carbon fibers. Such an approach significantly reduces energy consumption and harmful gas emissions compared to traditional high-temperature pyrolysis. Furthermore, research in the field of carbon nanotubes opens up new possibilities for creating fibers with improved mechanical and electrical properties. For example, a team of Chinese scientists developed double-walled carbon nanotube fibers using a dry jet wet spinning method, providing high electrical conductivity, up to 86% of copper's conductivity, tensile strength, and high toughness. These fibers demonstrate durability even after 5,000 bending cycles, making them promising for the aerospace industry and energy storage. Other innovations include the use of computer modeling and simulations to predict the properties of new materials and accelerate development. The company 3M, for example, uses ultraviolet, electron beam, and laser irradiation to create high-precision structured materials that enhance the strength and stiffness of carbon fiber-based composites. Developments are also underway for new technologies to reduce cost and improve the environmental friendliness of production, particularly using waste from the pulp industry as raw material, which reduces industrial waste and makes the process more sustainable. In the future, further improvements in production technologies are expected, along with the emergence of hybrid composites with nanomaterials and the expansion of carbon fiber applications, from transportation and construction to energy and electronics. Recycling carbon fiber is currently a complex and important process, as this material is widely used in high-tech industries, but its waste is difficult to process due to the complex structure of composites. There are several main methods for recycling and reprocessing carbon fiber reinforced composites. Mechanical recycling involves shredding the waste and separating it into resin particles and short carbon fibers. The short fibers are used as filler in construction or for manufacturing plastics. This method is simple and environmentally friendly, but it damages the fibers, reducing their strength. There's also high-temperature pyrolysis. Waste is heated to 200,000 degrees Fahrenheit in an inert atmosphere. The resin decomposes into pyrolysis products, and the fibers are recovered. The process requires precise oxygen control to avoid damaging the fibers. There is also a fluidized bed option, where the resin decomposes in a stream of hot air, and the fibers are separated by a cyclone separator. Microwave-assisted pyrolysis involves irradiating the waste with microwaves, which accelerates resin decomposition. The method is simple and effective, requiring less equipment. Chemical recycling, or solvolysis, involves dissolving the resin in special solvents, such as nitric acid with alcohol or supercritical fluids, allowing the fibers to be separated without damage. The fibers retain their length and strength, but the method is expensive and currently mostly laboratory-based. Other recycling methods for this fiber include radiation exposure to break down the matrix, ultrasonic treatment, and the development of new chemical reagents to separate the composite components. As you can see, the bigger challenges right now lie not in producing the material, but in recycling it. Recycling carbon fiber is crucial for reducing the environmental burden, as composite waste does not decompose naturally and takes up significant space in landfills. Modern technologies allow for the recovery of secondary fiber, which can be used in construction, plastics production, and even for reinforcing concrete structures. Every minute in the United States, over 1,000 feet of copper pipe is manufactured. But behind this seemingly simple component lies large-scale production, explosive temperatures reaching 2,000 degrees Fahrenheit, and even espionage investigations. From molten lava in furnaces to laser marking under ultraviolet light, each pipe follows a journey straight out of a movie about industrial superheroes. And did you know that some people are audacious enough to counterfeit copper just by painting its surface? This story is about how real pipes are made and how to distinguish the genuine article from a dangerous fake. Let's dive into a world where every second equals a ton of metal. It all begins underground, in the copper mines of Arizona or Montana, where hundreds of thousands of tons of copper ore are extracted each year. It's crushed, washed, purified, and the output is shiny granules of pure copper. These granules go into smelting furnaces, where temperatures exceed 2000 degrees Fahrenheit. Here, the copper transforms into molten lava. The molten copper is poured into long molds, so-called slabs, or ingots. They resemble thick orange beams, glowing white hot. These ingots are destined to become pipes, but there's still a long way to go. Pure copper in the form of ingots or cathode plates is loaded onto railroad flat cars, trailers, or even ships, and transported to rolling mills or pipe manufacturing plants. Cathode plates are thick metal sheets, approximately 3.3 inches by 3.3 inches, weighing up to several hundred pounds each. At the plant, the ingots or cathodes might first undergo additional remelting to achieve the required purity or desired shape, for instance, round billets for pipes. Then, they are heated and sent to the rolling mills. Rolling lines operate with machines boasting over 10,000 horsepower. The ingots are sent to rolling stands, machines weighing tens of tons. Giant rollers crush the hot metal, transforming it into long strips. The sight is incredible. The red-hot copper stretches out, sparks fly everywhere, and nearby, streams of water cool the metal, turning it into a shiny, almost mirror-like sheet. In modern workshops, all of this is controlled by computers. An operator sits in a glass cabin, similar to an airplane cockpit, monitoring dozens of screens. Here, every temperature, pressure, even the sheet thickness is under control. If anything goes wrong, the automation instantly stops the line. Now for the most interesting part. The copper sheets are cut into blanks. In plants where the copper sheets are still hot after rolling, powerful hydraulic or mechanical shears are used for cutting. They look like giant guillotines with massive steel blades. The sheet moves along a conveyor. An automatic sensor determines the exact cutting spot. The blades descend with immense force and slice off pieces of the required length and width. What do I mean when I say, with immense force? Sometimes it's tens of tons of pressure. All this happens in seconds, often while the sheet is still moving. That is, the line doesn't stop, and the guillotine cuts on the fly. For certain formats or thinner sheets, rotary knives are used. These are rotating steel discs that cut the copper as the sheet moves. It looks a bit like cutting pizza, only on an industrial scale. This method is suitable for narrow strips, or when the sheet needs to be cut, not only crosswise but also lengthwise. In modern factories, laser or plasma cutters are used for complex shapes or high precision. A laser beam or plasma arc heats and vaporizes the copper at the point of contact. This results in a perfectly smooth cut, almost free of burrs. Lasers are used for non-standard parts or when special geometry is required. After the main cutting, the blanks may pass through special edge trimming machines that remove irregularities, sharp edges, or excess material. The cut blanks are fed into drawing machines. This is a huge press that draws the copper through a steel die. The output is a perfectly round, smooth pipe. All this happens in mere seconds. The machinery operates at incredible speed. At large plants, like Mueller Industries, they can produce over 1.5 million feet of pipe in a single shift. That's, no lie, like the distance from Chicago to Detroit. Each pipe undergoes automatic inspection. Laser scanners search for microcracks and defects, and special robots select samples for additional testing. After being drawn from the red-hot die, the copper pipe is still hot, flexible, and prone to deformation. To quickly give it stability, the pipes are automatically directed onto a conveyor, leading to special cooling pools. Inside is cold water, which creates clouds of steam upon contact with the incandescent metal. This sharp temperature drop locks the pipe's shape, preventing it from bending or losing its geometry. Cooling takes only a few tens of seconds, but is crucial for quality. Next, the pipes arrive at the precision cutting table. Here, they are met by automated robots equipped with cutting discs or hydraulic knives. They measure the length with laser sensors and quickly cut the pipe according to the standard. For example, 10, 20, or 40 feet, depending on the order. Cutting accuracy reaches tenths of a millimeter, and the speed is up to several hundred pipes per hour. After this, the pipes undergo quality control. Laser scanners check the external appearance. looking for cracks, burrs, or other defects. Rejected pieces are automatically sent back for remelting. Those that pass inspection continue along the conveyor to the marking machines. Here, a laser mark is applied to each pipe. It encodes the production date, batch number, sometimes even a QR code for tracking. This allows for precise identification of each pipe in case of claims or the need for quality analysis. After marking, the pipes might still be slightly damp from the cooling water. To prevent corrosion and ensure a perfect appearance, they are moved into drying chambers. These are tunnels with powerful fans and heating elements. In just a few minutes, the moisture completely evaporates and the pipes acquire their characteristic copper sheen. Next comes the packaging stage. Here, robotic manipulators come into play. They pick up the pipes using suction cups or grippers, very carefully stacking them into bundles of 10, 50, or 100 pieces, depending on the diameter and length. The robots work with surgical precision to avoid damaging the pipe surface and prevent deformation. After forming, the bundle is secured with metal or plastic straps for reliable fixation. Some plants add protective film or cardboard inserts to prevent scratches during transport. The finished bundles are automatically moved to warehouse platforms. There, each batch receives a logistics label with all the data about the manufacturer, dimensions, production date, and final recipient. Then, loading onto trucks or railroad flat cars. Everything happens as quickly as possible. A modern plant can prepare thousands of tons of pipe for shipment in a single day. Thanks to automation, this stage minimizes human involvement, ensures safety and accuracy, and guarantees that the pipes will arrive at the customer in impeccable condition. Oh right, I promised to tell you about the spy games. This is a real detective approach in manufacturing. Due to the high price and constant demand for copper, temptation arose for unscrupulous manufacturers or intermediaries. They started counterfeiting markings and passing off cheaper alloys, or even other metals as pure copper. Fraudsters became so brazen that they began forging documents and selling bootleg goods under the guise of reputable brands. Counterfeits can be dangerous. They often fail under pressure or corrode faster. A rupture in such a pipe can cause accidents, flooding, or fires. Counterfeiting scandals have occurred in many countries when it was discovered that a copper pipe actually contained only a thin layer of copper, with cheap metal inside. Manufacturers spent years building their reputations, and counterfeits under their name could lead to mass recalls and lawsuits. Therefore, pipes are now marked with invisible inks visible only under ultraviolet light. This helps combat counterfeiting. Imagine taking the air you are breathing right now and turning it into a substance that can freeze ice cream in 3 seconds and make a banana tough enough to hammer nails. This is not magic. It is liquid nitrogen. Every second, it is used in medicine, science, the food industry, and in some top-secret experiments. Temperature, -321 degrees Fahrenheit. One sip and you lose part of your stomach. One breath and you unlock tomorrow's technology. How does the coldest substance on Earth get made from regular air? How is it transported, stored, and used? And why can it save or destroy? Watch closely and prepare to be amazed. It all begins with air. Yes, the very same atmospheric air that surrounds us. This happens inside industrial air separation units. These systems come in all sizes, from massive factory installations to mobile units for medical use. Air is sucked in using compressors. Then, it passes through filters. First, coarse filters that remove dust, insects, and pollen. Next, fine filters get rid of moisture, carbon dioxide, and other impurities. Once cleaned, the air is compressed using powerful machines, increasing both pressure and temperature. Then, it is gradually cooled in heat exchangers. When the high-pressure cooled air moves through a narrow nozzle into a low-pressure chamber, it expands rapidly. That sudden expansion causes a major drop in temperature. This is the key moment. The gas becomes cold enough to start condensing into a liquid. This process repeats several times. Each cycle drops the temperature further. Eventually, nitrogen reaches its liquefaction point. This technique does not work with every gas, but it is perfect for nitrogen. Thanks to this, we can create liquid nitrogen from ordinary air. Once the air is chilled and liquefied, it goes through fractional distillation. This process separates the liquid mixture into components based on their boiling points. Inside a special distillation column, the liquid air is gently reheated. Nitrogen has the lowest boiling point, around -320 degrees, so it evaporates first and rises to the top. Oxygen boils at -297 degrees, so it evaporates later and does not climb as high. Argon, with a boiling point around -302, settles somewhere in between. The column forms a thermal gradient, colder at the top, warmer at the bottom. The gases evaporate and condense over and over, becoming purer with each cycle. It all works without additives, automatically, and with minimal losses, thanks to precisely managed pressure and temperature. Since nitrogen makes up roughly 78% of air, extracting it takes powerful equipment, a complex network of pipelines, and exact temperature control. Once separated, liquid nitrogen is stored in special vessels, cryostats, or Dewar flasks, which look like futuristic thermoses. These vessels keep temperatures low and prevent evaporation. They are not just metal barrels. They have double walls with a vacuum in between to block heat. Some also include reflective coatings to minimize radiant heat loss. These containers can preserve liquid nitrogen for several days to several weeks, depending on volume, insulation, and how often they are opened. Often, nitrogen is used right on site. For example, medical facilities use liquid nitrogen for cryopreservation of cells, embryos, vaccines, and tissues. In the food industry, it is used for flash freezing. Contact with liquid nitrogen instantly freezes food, locking in texture, taste, and shape. But when it needs to be transported, preventing evaporation is critical. That is because nitrogen quickly turns back into a gas. Portable dewars, cryotanks, and cryotank trucks are used. Small dewars are handy for labs and clinics. Cryotanks are massive, like giant gas tankers, and are hauled by trucks with special mountings and ventilation. Cryotank trucks are purpose-built vehicles with insulation and pressure regulation to avoid explosions from expanding gas. Sometimes, liquid nitrogen is produced directly on site, at large research centers or hospitals, to avoid reliance on deliveries. How did humanity tame one of the coldest, most inert substances on Earth? It all began with nitrogen. Discovered in the year 1772 by Scottish chemist Daniel Rutherford, who was studying air and found a gas that could not sustain fire or life. That was nitrogen, colorless, odorless, inert. But liquefying it required cold and pressure, and humanity needed more than 100 years to figure that out. The first liquid nitrogen was produced in 1883 by Polish scientists Zygmunt Wroblewski and Karol Olszewski. They built a system that cooled air so much that nitrogen, its main component, turned into a liquid. That was a breakthrough. In the 20th century, cooling tech advanced fast. Scientists improved gas liquefaction methods and eventually developed the Joule-Thomson cycle, which relies on pressure drops to efficiently liquefy gases. In the 1930s and 50s, liquid nitrogen made its way into industry and medicine, starting in labs, then into surgeries, biobanking, and physics experiments needing ultra-low temperatures. Today, liquid nitrogen production is a global-scale operation. It is made in massive air separation plants around the world. What was once just background gas, making up almost 80% of air, has become a superstar of industrial science. Some chefs even make ice cream live, pouring cream into a bowl, adding liquid nitrogen, mixing, and voila, instant dessert. The cold is so intense, it freezes the treat in seconds. Dip a banana in liquid nitrogen for a few seconds, and you can hammer nails with it. Seriously. Want to try? Inhaling cold nitrogen vapor can temporarily change your voice, like helium, but deeper. But do not try this. It is dangerous without protection and special equipment. Some people have dipped old socks into dewars of liquid nitrogen. Result? The fabric becomes brittle like glass and crumbles in your hands. A perfect way to destroy evidence. If you are a sock. Pour liquid nitrogen on a warm floor, and it turns into a dramatic cloud. It vaporizes instantly, making you feel like you are stepping through a Hollywood portal. What should you never do with liquid nitrogen? Even if it looks cool, never stick your hand into it. Online videos show people dipping fingers and pulling them out unharmed. That is the Leidenfrost effect. A brief protective vapor layer forms around the skin, but if you hesitate for a second too long, hello frostbite, do not try it. Seriously. Never drink it. Yes, that happened too. In several restaurants, smoky desserts were served with a drop of liquid nitrogen. One careless guest sipped before it had fully evaporated and lost part of their stomach, literally. Afterward, several countries banned such stunts. Do not pour it on your bathroom floor. The vapor looks cool, sure, but tiles can crack from thermal shock. Plus, the risk of suffocation in a small space is real. Nitrogen displaces oxygen. Do not pour it in the toilet. Not because it will definitely break, but it might. And because pipes can burst. Some TikTokers have proudly frozen their plumbing. Utility crews must love them. If you are not an engineer or a molecular gastronomy chef, do not try freezing food or fruit from the inside. Liquid nitrogen can rupture the skin and explode in your hands, especially with high moisture items. So yes, liquid nitrogen is amazing, but it is also incredibly dangerous. Respect the frost. Every year, over 2,200 million pounds of edible insects are produced worldwide. They are dried, ground, and added to cookies, snack bars, and even cheese filled with live larvae. The biggest farms are now being built across tens of thousands of acres, not just in Asia, but in Canada, Spain, and the United States too. Crickets, beetles, locusts, they are crashing into the future of food. Why? They are cheaper than meat, healthier than fish, and 100 times more eco-friendly than beef. In this video, we will show you what these farms look like, how insects are raised, and how they end up on our plates. Right now, several companies are competing for the title of the world's largest edible insect farm. Let me tell you a bit about each. In January of the year 2025, the company Tebrio began building a farm called O Farm in Salamanca. When finished in the year 2028, it is expected to cover over 22,000 acres and produce more than 220 million pounds of insect-based products annually. In September of the year 2023, the company Cricket One launched Asia's largest cricket processing plant in Binh Phuoc province. The initial capacity is about 2,205,000 pounds per year, with plans to scale up to over 22 million pounds in 5 years. Hold on, let me take a sip of water while the insectophobia exits our chat. In London, Ontario, Aspire Food Group built a 150,000 square foot facility, considered the world's largest cricket processing plant. The title of largest edible insect farm changes constantly due to the rapid growth of this sector and new projects launching all the time. You might ask, why? Or maybe you are speechless already. But here's the thing. In more than 100 countries, insects have been part of the diet for centuries. For people in Thailand, Mexico, and parts of Africa, it is just normal food. In Thailand and Laos, the beetle Lithocarus indicus is used as a spice. Its internal extract tastes like green tea and mint. People squeeze it like a lemon, just imagine. A little beetle on your salad, and you are good to go. In Sardinia, there is a cheese with live larvae. It is officially banned, but highly prized by locals. It is made from sheep's milk, and the larvae actively move and digest the cheese, giving it a soft texture and sharp flavor. People eat it with the larvae, alive. If the larvae are dead, the cheese is considered spoiled. In Cambodia, fried tarantulas are a popular delicacy. They are said to taste like a cross between crab and chicken. People break off the legs, remove the venomous fangs, and enjoy a crunchy lunch. In Japan, tiny beetles are used in fermenting traditional foods as natural preservatives. For example, in making soy sauce or fermented paste, a bug-based microflora is used to give the right smell and texture. In the European Union, yellow mealworm larvae flour is now legally approved for food. It is high in protein and nearly tasteless. So now there are breads, cookies, and pasta made from insect flour. In many countries, insects are not served as, "Hey, here is a fried grasshopper with legs," but are ground into flour and added to snacks or protein bars, looking just like regular food. Insects are rich in protein, iron, omega-3, and vitamins. Many are as nutritious as meat. For example, crickets contain 70% protein by weight. Insects reproduce quickly. For farmers, this is a win. One full cycle takes just weeks, not years. Unlike cows or pigs, insects need far less water, feed, and space. They also emit fewer greenhouse gases. Perfect for the planet. Officially and legally, the most commonly farmed insects are crickets, mealworms, and locusts. Farms usually specialize in one insect species for efficiency. This helps streamline operations and reduce management costs. Insects have different needs: temperature, humidity, and feed. So it is easier to focus on just one species per farm. However, some farms raise multiple insects, like combining crickets and mealworms, or create zones for each, if it makes economic sense. A cricket farm is a structured system where insects are raised specifically to produce protein used in food, feed, or even the cosmetics industry. Such a farm can be a small business or a large commercial facility, producing thousands of tons of protein each year. The first thing a cricket farm needs is a properly equipped space. This could be large containers or racks with boxes or trays for breeding and raising crickets. Temperature and humidity are critical. It should not exceed 90 degrees Fahrenheit, and humidity should be between 50 and 70%. Crickets also need a light cycle, so artificial lighting is sometimes used to maintain optimal conditions. Choosing the starter insects is key. Special breeding cages are set up where adult crickets reproduce, and the eggs are transferred to other containers to develop. Crickets go through several life stages: egg, larva, nymph, and adult. This process takes 6 to 8 weeks. During their lives, crickets consume a lot of feed. Typically, this includes wheat bran, vegetables, fruits, and special mixed feeds, providing all necessary nutrients. They eat actively, so farmers must regularly replace food and check its quality to prevent disease outbreaks. Once crickets mature, they are harvested. Farms use special equipment to separate adult crickets from the substrate and sort them for further processing. Usually, crickets are either dried or frozen before being turned into powder. That powder is then used to make feed, energy bars, or even dietary supplements for humans. A critical part of the farming cycle is cleaning the breeding containers to prevent pests and disease. After harvesting, farmers clean all trays, change substrates, and sometimes add new insects to replenish the population. Proper waste management is also important, since leftover food and insect waste must be disposed of safely. After crickets are processed, they are either dried or turned into powder, depending on the product being made. If it is animal feed, the insects are simply dried and crushed. For food supplements, the process is more complex, involving special machines to retain all the nutrients. Technology on these farms is constantly improving, because this is a business built for an eco-friendly and sustainable future. A farm like this can be fully self-sufficient, using organic waste for feed, making it both economical and green. Mealworms are another popular insect raised for protein. They have great potential in the food industry, for both animal and human consumption. Mealworms belong to the beetle family, and are often farmed because they are easy to raise and high in protein. Mealworm farms usually have several rooms or trays where ideal conditions are created for reproduction and growth. The perfect temperature is between 170 and 186 degrees Fahrenheit, and humidity must stay low to avoid mold or disease. They need dim lighting, so these farms often operate in low light environments. The process starts with introducing the starter material, mealworm eggs, which are placed in containers with substrate for incubation. Eggs develop into larvae over several weeks. These larvae are protein-rich and used for animal feed or ground into food supplements. After 2 or 3 months, larvae transform into pupae, then into adult beetles. For healthy development, mealworms need moist, fiber-rich substrates like wheat bran, cornmeal, or even vegetables and fruits. They feed actively on the substrate, which also helps recycle organic waste. Farmers must regularly change the feed, check moisture levels, and inspect for parasites. Yes, you read that right. Mealworms can have their own parasites. I will never look at protein the same way again. Once the larvae are big enough, they are collected, by hand or with machines. After harvest, they are either frozen or dried. The dried mealworms become the base for pet food or protein-rich human food products. After harvesting, containers must be cleaned of leftover feed, insect waste, and dead bugs. Clean environments are crucial. Substrates should be regularly replaced to prevent harmful microbes. Locusts are another insect raised for protein, but they are much more demanding. Locusts are your high-maintenance girlfriend in the insect world. They need attention. Farms for locusts often include large greenhouses or special buildings that mimic natural habitats. The temperature must be around 85 degrees Fahrenheit, and humidity should not drop below 50%. They also need plenty of space to reproduce and grow. Locusts reproduce by laying eggs, which are incubated in warm, moist conditions. Once hatched, the nymphs look like adult locusts, but without wings. They need time to grow into fully mature insects. Locusts are herbivores, so farms feed them grasses, leafy greens, and vegetables like cabbage or carrots. Proper nutrition is key to a healthy population and high protein content in the final product. Now the girlfriend comparison ends, because once locusts reach maturity, they are collected, separated from the substrate, and processed. Usually, they are frozen or dried. After drying, they can be turned into powder for animal feed, food additives, or even cosmetics. Like with other insects, locust farms must be cleaned regularly to prevent disease and maintain healthy conditions. The production models for mealworms and locusts are similar, even though their needs and diets differ. This allows farms to maintain consistency and ensure high-quality products. So, what will you choose? Potatoes, or some surprisingly healthy insects?